Okay, you see the whiteboard, yes?
Yes.
Okay, so now what conclusions do we have until now? So if we want a method to study the monotony and to find the local extrema of a function f, we have the following algorithm. First, compute the derivative, then solve the equation f prime of x equals 0. The solutions of this equation are called critical points. And third, make the table of variation which contains the most important information, which is the sign of the derivative, as we remember from what we discussed in the first hour. So the table of variation has 3 rows. On the first row, we have the domain of the definition. So x belongs to some domain, whatever is that domain. Suppose it is, for example, the set of real line, the set of real numbers, but not necessarily. When we solved this equation, we found here some solutions. Let's say 3 solutions, for example. So the derivative is 0 at these points. And now on every of these, on each interval here, the derivative has a sign. We decide this sign by computing the value of f prime at some particular points in every interval. For example, suppose here it is positive, then it is positive again, then it is negative, and then positive. What's the conclusion about the function f? On an interval on which the derivative is positive, the function f is, please tell me how. According to our previous, yes, please?
Positive?
No. Anyway,
no.
We are not interested in the sign of the function. We are interested in the monotony. If the derivative is positive, the function f is, look to your notes.
Oh, it's negative.
We ended the first part with a conclusion. That conclusion is the following. I shall write it again, but so the conclusion was this. F increasing
increases. Doesn't it
means the derivative is
greater than 0?
Greater than 0, yes. This is the most important thing in calculus. What we did in the first hour is the core of calculus. Yes. And if f is f decreasing, this is equivalent with a negative derivative. Of course, everything under some appropriate hypothesis, and we made them already. We know f has a derivative at every point, and so on. So, because on this interval, the derivative is positive, the function f will be increasing. And here it takes the value f of x1. Then on the interval x1, x2, the derivative is still positive. The function is increasing. It continues to increase. It continues to increase up to a value f of x2. And now on the following interval, the derivative is negative. So the function will be decreasing to some value f of x3. And then the derivative is positive again. So the function is increasing again. And here on this table, we have all the informations about the behavior of the function f. Where is it? Increasing or decreasing, and the extreme values. For example, x2, is it local minimum or local maximum?
Maximum.
It's a local maximum, of course, because the function is increasing and then it is decreasing. x3, it's what?
The minimum.
It's a local minimum. The function is decreasing and then it is increasing. So it's a local minimum. What about x2? At the left, the function is increasing. It arrives here. And then what it does? It is increasing again. So it goes like this. So x1, is it a local minimum or a local maximum?
No.
No. So on this hypothetical table of variation, we have two local extrema. x2, which is a local maximum, and x3, which is a local minimum. x1, it is a critical point because the derivative vanishes at x1, and we remember that the points where the derivative is vanishing are called critical points. They are important, but it is not a local extremum, not a local minimum, not a local maximum. Okay, this is the main, let's say, part of what we call the study of functions by using derivatives. So we discovered the behavior of the function f, monotony and local extrema, by using the sign of the derivative. So the most important information here is the sign of the derivative. To know if the derivative is positive or negative is the main information when we study a function. And we have to follow this algorithm. You will see that this algorithm, can be generalized to functions of several variables. That will be our next goal at the lecture and the main theme for the final exam. But that is for several variables. Now we are talking about functions of one single variable. We must know very well this problem and then move to several variables. Okay, let's do some, if you have some questions here, I'm waiting, and we continue with some applications. So this was the theory. Resuming the theory is the following. The sign of the derivative gives us the most important informations about the behavior of a function. Behavior means if it is increasing or decreasing. Okay. If you have any question.
No.
Okay, let's do some exercises. Let's consider f of x equals x over x squared plus 1. Now, the domain of definition of this function, in general, the domain of definition is obtained by putting some conditions. The usual conditions are about denominators. The denominators must be different from 0, but this denominator is always different from 0. Other conditions are related to square roots and logarithms. We don't have. So here, this function is defined on the entire set of real numbers. And we would like to know the monotony and the local extrema. So this is the general question. And in order to do that, we must follow exactly the previous algorithm, yes, those in 3 steps, and finalize everything with a table of variation, which will give us the answers. Please do it. So the first step was to compute what? Previously, we have an algorithm, a method in 3 steps. The first step was to compute
the derivative.
The derivative. Please compute the derivative. You told me that you know the rules to compute derivative of functions of one single variable. So compute the derivative of this function. Okay. Did you compute it?
Oh, yes. I have the same.
You have the same value, yes, as here.
Yes.
Okay. Now the next step is to do what?
To solve the equation.
Solve the equation f prime of x equals 0.
Yes.
Solve it.
It will be x1 is -1 and x2 is 1.
So the solutions are x1, 2 equals plus and minus 1, yes?
Yes.
Okay, now the next step.
The sign table.
And now it's not a sign table, it is it has 3 lines, it's not sign there. It is the sign of f prime and it is the behavior of f, monotonia. Okay, it's the sign table for the f prime, but it is more complex, this table. It's not just the sign of f prime, as we can see. Okay, the variation table, this is how it is called, the variation table, which gives us the behavior of the function f. Now, the domain of definition is written here. Yes, it's minus infinity, infinity. On this, here, attention, we complete this table as follows. First, we fill in the first row. The first row contains the domain and the critical points, which are -1 and 1. That's over with the first row. The second row, this is 0, and here is 0. Because this is how we found them. We put the condition f prime of x equals 0. And now the sign of f prime. You can use f prime, it is written here. Attention, here the denominator is obviously positive. So is the sign of the numerator. You can find the sign here in 2 ways. By using the sign of the quadratic function, we know the theory of the sign of the quadratic function, or you can check the sign on some particular points on each interval. You can do it, so you can do it in 2 ways. Doesn't matter how. Just tell me now the sign on the interval minus infinity minus 1. F prime is positive or negative?
I'm sorry. So we need to replace the x with the...
Look, attention. On the interval minus infinity minus 1, so when x belongs to this interval, the function f prime, which is written here, takes a sign, positive or negative. We have to decide. Yes? We can do it in two ways. In a theoretical way, which means to know the sign of a quadratic function, because we learn about it and we already use it previously, if you remember, or in a not theoretical way, take an arbitrary value for x in the interval minus infinity minus 1, compute f prime of that number you will take, see what value you get, see what sign has that value, and then the sign at that value will be the sign on the entire interval minus infinity minus infinity. So the second method could be a sort of verification or something like this. You understand what I'm trying to tell you?
Yes.
Okay, so what's the sign of f prime on this interval? You don't know what the sign means? It is positive or negative? That means the sign. The sign, yes, the sign. For example, -5, it's a negative number.
Yes.
4,
yes.
it's a positive number. That means the sign.
It will be plus.
How? Okay, it's plus, but tell me how you found it.
On the first lesson, we said that if so, the sign on this interval will be the sign of a in our quadratic function.
Okay, so you want to use the theory of the quadratic function. Here we are talking about what quadratic function? G of x equals what?
1 minus x squared.
1 minus x squared, very well. We are talking in general about the quadratic function g of x equals ax squared plus bx plus c, yes? So this is, okay, so who is a for us?
So a minus 1.
A is -1. B is?
1.
No, B is 0.
Oh,
and C is?
C also 0.
If C would be 0, then the function would be minus x squared. Yes, if you replace here A by -1, B by 0, and C by 0. So you don't get 1 minus x squared. So think to, attention. Think to the values of A, B, C. What values would you take for A, B, C if you replace them here to get this?
Yeah, so A minus 1, B 0, and C 1.
Okay. So C it's 1, of course. And now these are and now tell me the value of 1 minus x squared on the interval minus infinite minus 1 according to the theory of the quadratic function.
So it's minus.
It will be negative. Okay.
Yes, negative.
Now, another way, the second way you can do it is the following. Tell me an arbitrary number from the interval minus infinity minus 1. A fixed value.
-2.
-2, okay. Now compute f prime of -2 and tell me what do you get. What did you get?
Will not it be just 0?
So if we compute the value of f prime at -2, here is my computation. Check if you have the same.
So we need to. Oh, I did it wrongly. Yes, I substituted it just in the numerator.
Okay, but the numerator doesn't give you 0 because you told me something with 0. If I heard well, maybe not. I don't know. If you substitute only on the numerator, you get -3. Now, attention. Be careful what I'm saying now. The derivative f prime is written here. Don't make a confusion with the with the moment where we solve the equation f prime of x equals 0. This has nothing to do with that. This is the value of the derivative. And we want to know the value of the derivative at the point -2. This was your choice, yes? Okay, let's compute the value of the derivative, which is written here, at -2. It's an elementary question. It gives you what?
Yes, it gives a -1.
So it's -3/25, which is negative. It's the same value we got theoretically by using the sign of the quadratic function. Now, do the same for the interval -1, 1. But I would like to do it in two ways. Theoretically, from here, and then by choosing an appropriate value for x, that means a fixed value in -1, 1, compute f prime of that value and see what you get. You must get the same sign in both ways, but please do it. According to the theory of the sign of the quadratic function, what sign we have on -1, 1? The theory says that you have a sign which is opposite to the sign of A.
Yeah, so it's positive.
It's positive. Now, the second way.
I also got positive.
What value do you take?
1/2.
Okay, but a simpler one would be 0, but it's 1/2, it's okay. So it's positive. On the interval 1 infinity, what is sign?
Again, negative.
Okay, negative. Okay. And now what's the conclusion? About the behavior of the function.
On the first interval, it's decreasing, then increasing.
Then increasing and then decreasing again. Now, let's see the values of f at the point -1 and at the point -1. So here, please compute f of -1 to put here the value. What's the f of -1 equals what?
0.
How it can be 0? I don't understand. You get always 0. The only value you get all the time is 0. It's not possible. If you replace x equals -1 at f of x, you get -1 over 2 of yours. Okay,
I'm sorry, I'm again looking at the wrong equation.
Okay, so -1 over 2. And the value of f at 1 is?
Also 1 over 2.
No, it's not also.
No, not also, just 1 over 2.
1 over, okay. Okay, in this moment, we know what about this function? We know where is it increasing or decreasing, yes? And also we know the local extrema. Who are the local extrema?
-1 over 2
X
is...
we always say the x coordinate. When x equals -1, is it a local minimum or a local maximum?
Minimum.
It's a local minimum. While x equals 1, it's a local maximum.
Maximum.
Okay. So we answered to the two questions about the monotony and the extrema. Yes? Of course, if we want to know much more about the behavior of this function, the only thing we need to know are the limits of the function at -infinity and at infinity. This is not connected to the question of monotony and local extrema. But if we want to know the entire behavior of the function, it's good to compute also the limits from to -infinity. And these are both 0. Yes, these are both 0. And okay, about computing limits, if you want, next time when you will be present here, we can I put already some materials on Microsoft Teams about computing limits. And if you read them, you will see how we can compute limits. And we may have here also a discussion about computing limits. So but that is another subject. Yes, okay. So this is the behavior of the function. If we want now, we can sketch the graph of this function. At -1 and at 1, it has extrema. Here, the value at -1, it's -1 over 2. The value of f at 1, it's 1 over 2. So the graph starts from the point -infinity 0, which means here it's close to the x-axis. It goes, yeah, it passed through 0 because at 0 it takes the value 0, f of 0 equals 0. That is an important point because it is the origin of the axis. It is increasing to 1, and then it is decreasing to the value 0. So the graph of the function looks like this. But here there is more information. Not only monotony and extrema, but the most important information is contained in this table, yes? Monotony and extrema. Okay, so this is the algorithm. Let's try another exercise. For example, let's consider this function f of x equals e at x at minus x over, let's say, x plus 1. Okay, this function is defined on what set? We must put the condition x plus 1 different from 0. So x is different from minus 1. That means the domain of definition is a union of the interval minus infinity minus 1 together with minus 1 infinity. So at minus 1, the function doesn't exist, because if you want to compute f of minus 1, it will be meaningless because you get 0 on the denominator. Okay, now let's start our algorithm. So first we need to compute the derivative. Please compute the derivative.
It will be x times exponential in power of minus x plus 2 exponential in power minus x divided by x plus 1 and all in power 2.
Okay, let's check it. So the derivative will be on the denominator we have x squared plus x plus 1 squared, and above we have minus e at minus x times x plus 1 minus e at minus x. Yes? This is the formula for the ratio.
Yes.
And so below we have x plus 1 squared, and above we shall have minus e at minus x times x plus 2. Is it okay? Because if you take here a common factor minus e at minus x, we get x plus 2, yes? In the parentheses.
Mm-hmm.
Is it okay, or you have doubts? Because if you multiply here, if you multiply, it will be minus x e at minus x minus e at minus x minus e at minus x, which means minus x times e at minus x minus 2 e at minus x, which means minus e at minus x times x plus 2.
Oh, yes.
That's why we got here x plus 2. Okay?
Okay. Yes.
Okay, now the second step is to solve the equation f prime of x equals 0, which means minus e at minus x times x plus 2 equals 0. Here we have e at minus x equals 0 on one hand, on the other hand x plus 2 equals 0. Now, Now, E at minus x equals 0. What do you know about this equation? It has no solution.
Yes, it doesn't.
The exponential doesn't take the value 0. Yes? So, again, the equation A at x equals 0 has no solutions. Okay, so and from here we get x equals minus 2. So the function has only one critical point, which is minus 2. Clear?
Yes.
And now the third step, consider the table of variation. Okay, now attention, here the domain of definition is no more the entire set of real line, is the set without minus 1. So first we put here minus 1 and we put a vertical line, yes, at the derivative at the function, which this is the sign, this is the convention to show that at the point x equals minus 1, the function is not defined. Minus 1, it is not in the domain of the definition of the function. Now we put the critical points. We have only one critical point, minus 2, which is at the left of minus 1. And here f prime is 0. And now we have 3 intervals, 1, 2, 3. On each of these intervals, the derivative has a sign. Please find that sign. The derivative, attention, it's written here.
It should be always positive in exponential function.
No, don't. That is not only the exponential there.
Oh, therefore, okay.
So it is much more complicated. The derivative is not an exponential. It is something very complicated. It is a multiplication between an exponential and a function of degree 1. It has a denominator. So don't simplify too much, because things are not that simple. Take values. Tell me a value in the interval minus infinity, minus 2.
Minus 1. Oh, no, minus 3.
Okay, compute the derivative at minus 3. Compute it. The function f prime is written here. Tell me what you get, and let's look to the sign.
The sign will be positive.
So I obtained the value e at 3/4, which is indeed a positive number. So here it's positive. Now on the interval minus 2, minus 1. Tell me a number here.
It will be not possible to take like the exactly minus 2 or minus 1.
No,
yes, because
of course.
Okay.
Between them.
Minus 1/2.
Minus 1/2, it's not between minus 2 and minus 1.
Oh, yes.
Look here. -1/2 is here.
Yes, sorry.
Another try. A number between -2 and -1. Look, attention. If you have two numbers, A and B, and you want a number between them, the simplest way to take it is as follows. To take the arithmetic mean between them, the average. That means A plus B over 2. A plus B over 2, it's always exactly at the middle between A and B. So it is always between them.
-3/2.
-3/2. Please compute the derivative at -3/2, and let's see what we get.
Oh, I have the same.
So here we got
Negative.
Negative. And now on the interval -1 infinity. Tell me a number between -1 and infinity.
0.
0,
Can
very
we?
well. Okay, very well, 0. It's the best. F prime of 0. Please compute F prime of 0 and see what you get. We get -2, yes?
Yes.
So here the derivative is negative. The conclusion is that on the interval -infinity minus the function is increasing, then it is decreasing, and then it is decreasing. Yes? We now must compute the value of f at -2, which is e at 2 over -1, which is minus e squared. So here it's minus e squared. The value of f at -1 doesn't exist, attention. And this is the behavior of the function. We know the monotony, and we know that it has only one local extremum, which is a local, x equals to, it's a local what?
Maximum?
It's a, so this is a local maximum, yes? Okay. Okay, that's all. I have the record it's on the Microsoft Teams, and you can see it when you want. Okay,
Yes.
goodbye.
Okay. Thank you. Goodbye.
Hello.